Palladium hydride is a metal hydride crystal formed by palladium absorbing hydrogen, much like a sponge absorbs water. This use was first discovered in 1866 by Thomas Graham, whose work in diffusion led to him discovering that palladium absorbs a surprising amount of hydrogen. Palladium hydride can be formed at room temperature as H2 tends to just diffuse into palladium based on concentration. Additionally, palladium hydride's phases are interesting in that there's an alpha phase and alpha prime phase. Palladium hydride has a composition of hydrogen ranging from 0 to 38 atomic percent, depending on how much hydrogen is absorbed. Lower concentrations form the alpha phase, and higher concentrations form the alpha prime phase. However, for our purposes, we'll focus on just alpha. This phase develops as a single crystal with only alpha solid as its microstructures. For the diffusing hydrogen, defects are important in determining where to go. Hydrogen travels to areas undergoing tensile strain and away from more compressively stressed regions. This is especially important for surface defects that hydrogen most effectively transports itself on. We can prove this with math. More math. A lot more math. But that's too much math, so just trust us on this one. Pure palladium naturally has an FCC structure, and so does palladium hydride. This is because the alpha phase occurs when hydrogen diffuses through the palladium and embeds itself in random interstitial octahedral regions within the palladium, a result of being FCC. Here, the hydrogen is forming covalent bonds while the palladium maintains its metallic bonds, causing a mix of strength and interatomic strain. Once enough hydrogen is absorbed, the new interatomic potential is incredibly stressed. The palladium lattice must be expanded, and thus the alpha prime phase is formed with numerous dislocations due to the abrupt change. All things considered, this alpha phase of palladium hydride is incredibly interesting and relevant for developing hydrogen technology.